Hello students, for this video I am going to talk about antiderivative of a function. But before we proceed to the discussion of these antiderivative, let us first recall derivatives of a function by finding the derivatives of these given functions. Number 1, we have f of x is equal to 5x cubed minus 10x squared plus x. Number 2, f of x is equal to x squared times the quantity x plus 1. And then number 3, we have f of x equals the quantity x plus 1 divided by x squared. So let's go to number 1. So since we are given by this function, so for our solution for the derivative of f of x, we have f prime of x equals, we are going to use the notation for the derivative, that's d over dx, 5x cubed minus 10x squared plus x. Next is we will apply the sum and difference rule, which is applicable for these functions since this is a polynomial function. So we will have the derivative of 5x cubed with respect to x minus, we have the derivative of 10x squared with respect to x plus the derivative of x with respect to x. And since you already know the multiple power rule for the derivative of a function, let's go directly solving the derivative of 5x cubed. And that will be 5 times 3, 15. X raised to 3 minus 1 is 2. So 15x squared minus our 10 times 2, we have 20, and then 2 minus 1 is 2. So that's 20x raised to 1, or 20x, plus the derivative of x is equal to 1. So our f prime of x is equal to 15x squared minus 20x plus 1. For the second function, we have f of x is equal to the product of x squared and x plus 1. So for our solution for the derivative of this function, we have f prime of x equals, since this is a product of x squared and x plus 1, let's apply the product rule. First, we are going to copy the first function x squared and then multiply that by the derivative of the second, which is x derivative of x plus 1. So you have x squared times the derivative of x plus 1 with respect to x, plus copy the second function, that's x plus 1, multiply that by the derivative of x squared. So let's find the derivative of these respective functions. We have first copy x squared and then multiply the derivative of x plus 1. So derivative of x is equal to 1. Derivative of 1 is 0. Plus copy x plus 1 and then derivative of x squared by power rule. We have 2x. Now let's simplify these expressions. We have x squared times 1 is equal to x squared. So we'll have x squared plus, we'll multiply 2x by x and then 2x by 1, which is equal to 2x squared plus 2x. And x squared plus 2x squared, that is equal to 3x squared plus 2x. So f prime of x is equal to 3x squared plus 2x. For this third example, we have f of x equals the quantity x plus 1 divided by x squared. So for our solution, we have to assign first, let's say, f and g for the numerator and denominator so that we can correctly apply the quotient rule for this given function. So let's say our small f of x be equal to x plus 1 and our small g of x, that's x squared. And we know that by quotient rule, our derivative of f and g is equal to gf prime minus fg prime divided by g squared. So for our solution in this case, f prime of x is equal to our g is x squared, so copy x squared, multiply that by the derivative of x plus 1 minus copy our f of x, which is x plus 1, times the derivative of x squared with respect to x divided by our x squared raised to the second power. Now, let us find the derivative of those expressions or functions in the numerator. So let's copy x squared and then derivative of x plus 1, that will be 1 plus 0, or let's just say 1 minus copy x plus 1, and then derivative of x squared is equal to 2x all over x raised to 4. Now we just have to simplify this. So we have x squared also minus 2x squared minus our 2x. I just have to distribute 2x in the negative x and negative 1. Let us copy the denominator, that's x raised to 4. And then, if we are to simplify the numerator, we'll have x squared minus 2x squared. That is negative x squared minus 2x divided by x raised to 4. So, as you can see, for our numerator and denominator, we have x for each terms, so we can factor out x and then in order to simplify the derivative, although we were able to get already the derivative of the function, but I think we can still simplify these one. So if we are to factor out x for both numerator and denominator, this will be negative x minus 2 divided by x times x cubed. So, we have negative x minus 2 over x cubed as the derivative of capital F of x. Now that we are done recalling the differentiation rules using these given functions, let us go to antiderivative of a function. So for this video, we are going to have three objectives. Letter A, illustrate the antiderivative of a function. Letter B, appropriately use rules of antidifferentiation. And letter C, compute for the general antiderivative of a function. So let me show you the definition first of antiderivative of a function. A function uppercase f is an antiderivative of the function small f on an interval if uppercase f prime of x is equal to small case f of x for every value of x in the interval. This means that we can say that the given function is the antiderivative of another function if the derivative of the first is the second function. But if we are concerned on the uniqueness of the antiderivative of a function, we can actually say that it is not unique because it can be antiderivative of many other functions. But there is a way for us to determine the more general or the general antiderivative of a function. So let us go back to the previous example earlier. We have the uppercase f of x is equal to 5x cubed minus 10x squared plus x. And we say that its derivative is small case f of x equals 15x squared minus 20x plus 1. So relating this to our lesson for this video, which is antiderivative of a function, we can actually say that uppercase f of x equals 5x cubed minus 10x squared plus x is the antiderivative of the small case f of x equals 15x squared minus 20x plus 1. Because, as you can see, if we are to find the derivative of the uppercase f of x, which is equal to the derivative of 5x cubed minus 10x squared plus x, this will yield to 15x squared minus 20x plus 1, which is equal to our small case f of x, right? So the derivative of the uppercase f with respect to x is equal to small f of x. So as mentioned earlier, the antiderivative of a function is not unique. So we can actually have other antiderivatives of our small case f of x. So let's say, for example, we have the function uppercase f of x equals our 5x cubed minus 10x squared plus x minus 5. So this can also be the antiderivative of small case f of x equals 15x squared minus 20x plus 1. So why? Because if you are to check for the derivative of capital F, we have capital F prime of x equals the derivative of this function with respect to x. This is equal to, let me just copy this one, minus 5 is also equal to, by power rule, let's go directly to the derivative of this function. We'll have 15x squared minus 20x plus 1 also, which is also equal to our small f of x. So looking at this illustration, the only difference that we will be having for multiple possible antiderivative would be due to the constant term. Okay? Even if you change the constant with a positive, a negative, or radical numbers, or even fractions, their derivative is still 0, right? So if you have here plus 5 or minus square root of 5 or even 1/5, the derivative of this constant is still 0. So this is because by our topic number 4, our rules in differentiation, the derivative of any constant is equal to 0. Let us consider another example for the illustration of the antiderivative of a function, especially when it comes to the uniqueness of the antiderivative of a function. So as mentioned earlier, we can have more than two or three antiderivatives. So let's say, for example, we are asked to solve for the antiderivative of cosine x. And in this illustration, we have three possible answers. Okay? We have the uppercase f of x equals sine x because the derivative of sine x is cosine x. We also have f sub 1 of x, which is equal to sine x minus 1, because the derivative of sine x is equal to cosine x, and then derivative of negative 5 is 0. Same with sine x plus 100. Its derivative is also cosine x. Alright? So these three are just some of the possible answers. We have a lot more to generate for these function small f of x equals cosine x. But the main concern is that would that mean we will be having different answers for this question? Okay? Do we expect to have different answers when we are dealing with antiderivatives of a function? So the answer is no. We can actually have a way of representing our answers as one. And that is now where the concept of general antiderivative will come in. So we say that the general, let's say general antiderivative of a function is the general way of representing all possible antiderivative of a function. So for instance, we given small f of x equals cosine x. So how are we going to represent generally the antiderivative of a function? Okay? So let me just write here for the general antiderivative of a function, that will be the uppercase f of x equals the derivative of the function, let's say derivative of cosine x, that will be equal to our sine x. Okay, antiderivative of cosine x, that will be sine x plus our constant, wherein c is any real number. So this c is our arbitrary constant. Okay? So for us to show the all possible antiderivatives of a functions. So these possible answers are what we called particular antiderivatives. But since we're dealing with general antiderivatives, the general way of writing the antiderivative of a function, we call that the general antiderivative. These constants are represented by our arbitrary constant represented by C. But if we have one specific constant, then we call that again the antiderivative of a function. Let us proceed to this theorem with respect to the arbitrary constant, with respect to the antiderivative of a function. So if uppercase f is an antiderivative of small case f on an interval, then every antiderivative of small f on the interval is given by uppercase f of x plus c, where c is an arbitrary constant. So this is for the general antiderivative of a function. Alright? So since these all three functions, all three will lead to the same derivative, right? The derivative of these three functions will give you cosine x. So the only difference is their constant term. Alright? So we will be using the variable c to denote the arbitrary constant for the antiderivative of a function, particularly for the general antiderivative of a function. So now let us proceed to different terminologies and notations that we will be dealing on this lesson. First is antidifferentiation. This is the process of finding the antiderivative of a function. Second, this symbol, right, more like an S, but we call this integral sign, which denotes the operation of antidifferentiation. So whenever you see a symbol like this, okay, this means we are dealing with anti-differentiation. Then the function f is called the integrand. A while ago, we deal with the derivative and antiderivative of a function given by, let's say, cosine x. We had sine x minus 5, sine x plus 100. So our small f is what we called the integrand. Some other notations, we have if uppercase f is the antiderivative of small f, we will write the integral of f of x dx equals the uppercase f of x plus c. So we have again the integrand, and then our integral symbol or notation. So the symbol, the integral symbol and dx go hand in hand, and dx helps us to identify the variable of integration. So let's say, for example, we have this notation. We have the integral of f of x dx. So we are dealing with a function, antiderivative of um, f with respect to x. Alright? So whatever the variable is here, that is our variable of integration. So somehow when it comes to the derivative of a function, we have the derivative of a function with respect to x. For this situation, we have the integral of f of x dx, meaning the variable of integration is with respect to x. The expression uppercase f of x plus c is called the general antiderivative of small case f. So meanwhile, each antiderivative small f is called the particular antiderivative of small f. Since you already know these terminologies and notations, let us proceed to this example. Alright, so we have now the notation for the antiderivative of a function. We have the integral of cosine x dx is equal to sine x plus c. First up, we have the integral sign. We also have our integrand. Okay, this is our f of x, the variable of integration, variable of integration, and then our general antiderivative, derivative of a function. And also, don't forget our arbitrary constant. Okay? So, we have these parts of our antiderivative of a function. Don't forget, because each of these notations plays a vital role in this process of antidifferentiation. Alright, let us now proceed to the different rules of antidifferentiation. For the first notation, we have the integral of dx is equal to x plus c, meaning, okay, we have here the integral of 1 dx, or more likely the integral of dx equals x plus c. Second, the integral of a dx is equal to ax plus c, wherein a is any real number. We also have the integral of x raised to n dx is equal to x raised to n plus 1 divided by the quantity n plus 1 plus c, wherein n is not equal to, it should be negative 1. Alright? So, we have here the power rule. This will serve as the power rule for the antiderivative of a function. We also have the constant multiple rule for integration, the sum and difference rule for the antiderivative of an algebraic functions. Aside from these general antiderivative of algebraic functions, we also have rules for the exponential and logarithmic functions. All of these formulas are found in our reading material. We also have the general antiderivative of trigonometric functions. We have for sine, cosine. We also have for tangent x, cotangent secant. We also have for secant x, tangent x, because if you can still remember, the derivative of secant x is secant x tangent x. So, for the antiderivative of secant x tangent x with respect to x, that will be secant x plus c. Alright? So, you also have for the integral of cosecant x cotangent x with respect to x, that's negative cosecant x plus c. Alright? So, aside from these trigonometric functions, you also have for inverse trigonometric functions. Let's go to these examples. For this first example, we have the integral of the quantity 12x squared plus 10x dx. As you can see, I enclosed 12x squared plus 10x in an a parenthesis for us to denote that this will serve as our integrand, because if we don't have parenthesis symbol, meaning the integral sign is only for 12x squared, and then for our dx, it is only for 10x. So if in case you are dealing with binomial or any polynomial functions, make sure to enclose them in a parenthesis. For our solution in this example, let me just write it here. We have the integral of 12x squared plus 10x dx. First is we are going to apply the sum rule for 12x squared plus 10x. So this will be the integral of 12x squared dx plus the integral of 10x dx. Again, don't forget to include dx for every term if you are going to apply the sum and or difference rule. Next will be, we can factor out 12 and then 10x. We're like applying the constant multiple rule. So this will be equal to 12 times the integral of x squared dx plus 10 times the integral of x dx. Alright? So since we have the integrand x squared and x, maybe we can apply the power rule in these terms. Applying the power rule, we'll have 12 times the quantity. As you can see, we're just going to add 1 in our exponent and then divide it by n plus 1. Since n in this first term is 2, we'll have x raised to 2 plus 1 divided by 2 plus 1. Then we're not going to add yet c. We are going to include c on the latter part of our solution. Plus 10 times the quantity. This is our x raised to 1 plus 1 divided by 1 plus 1. And then here we include plus c for the arbitrary constant. Okay? So, let me just go back to the rules. Ano ba yung ginamit natin for this particular part of our solution. Alright? So, if we are going to check for these general antiderivative of algebraic functions, it says that the integral of x raised to n, wherein n is any real numbers, dx is equal to x raised to n plus 1. As you can see, we add 1 for the numerator and then divide the exponent by n plus 1 and then plus c. Okay? So, going back here for our solution, we'll have 12 times the quantity x raised to 2 plus 1 divided by 2 plus 1 plus 10 times the quantity x raised to 1 plus 1 divided by 1 plus 1 plus c. Now, let us simplify these expressions. We'll have 12 times the quantity x cubed divided by 3 plus 10 times the quantity x squared divided by 2 plus c. And if we are to simplify 12 times x cubed divided by 3, this will give you 4x cubed plus 10 divided by 2 times x squared, 5x squared plus c. So this is the integral of 12x squared plus 10x dx. If you want to check, you can just get the derivative of this expression. So, check natin. Derivative of 4x cubed, that will be 12x squared, which is the same with this. Next, derivative of 5x squared is 10x, and then derivative of any constant is 0. Thus, the integral of the quantity 12x squared plus 10x dx is equal to 4x cubed plus 5x squared plus c. Let's go to the next example. We have the integral of dt t cube. So since we have dt, that means the variable of integration is t. Okay? We're not using x for this particular example. So for our solution, let me write it here. We have the integral of dt t cube. First up is we are going to um, expand the expression. We're not going to have t times t times t, but we will have to factor out dt first. Okay? So we'll have the integral of 1 times t cube dt. Okay? So, next is, as you can see in our table of integrals, we don't have particular rule for fraction whose exponent for the denominator is 3. So, what we're going to do here is apply law of exponent. We will write this as the integral of t raised to negative 3 dt. And after which, we will apply the power rule for integration. So this will be the integral of t raised to negative 3 dt. That's t raised to negative 3 plus 1 divided by negative 3 plus 1 plus c. Okay? So whatever it is na nasa new exponent natin, you have negative 3 plus 1, yun din yung i-divide natin sa kanya by power rule for integration. So if we are to simplify this, we'll have t raised to negative 2 divided by negative 2 plus c. And if you want to transform this into a positive exponent, we just have to apply the law on negative exponent, and this will give us 1 over, or the negative of 1 over 2t squared plus c. So this is the integral of dt cube. That's for our second example. Now, we go to our third example. You may pause from time to time and then try it on your own before you go to the video. Okay? So, for the third example, we have the integral of the quantity 5 cosecant x cotangent x minus 4 secant squared x dx. So, for our solution, okay, we have the integral of 5 cosecant x cotangent x minus 4 secant squared x dx. First is we will apply the difference rule. This is now the integral of 5 cosecant x cotangent x dx minus the integral of 4 secant squared x dx. Next is we will factor out the coefficient, numerical coefficient 5 and 4 in our integral notation. So this is now 5 times the integral of cosecant x cotangent x dx minus 4 times the integral of secant squared x dx. Next is we will go to our table of integrals and look for a formula or rule which pertains to these two integrands. Okay? For cosecant x, cotangent x, and secant squared x. So, let's go to maybe trigonometric functions. Right? So, hanapin natin dito yung particular formula or rule that we can use. So, we're looking for cosecant x, cotangent x dx. So, as you can see, we have 1, and that will be negative cosecant x plus c. Alright, so we're done with the first term. Second term is about secant squared x, and we have also 1 here. And the integral of secant squared x dx is equal to tangent x plus c. So going back to the solution, we have now 5 times the quantity. So for cosecant x cotangent x, this is equal to the negative of cosecant x. So negative cosecant x minus 4 times 4 secant squared x, we have tangent x. And then plus c. So this is now negative 5 cosecant x minus 4 tangent x plus c. This is the antiderivative of 5 cosecant x cotangent x minus 4 secant squared x with respect to x. I hope that this is clear to you, my dear students. Now, for our next example, we have the integral of the quantity x raised to 4 plus 6 divided by x squared dx. So for our solution, we have these rational functions, but since we don't have yet particular formula for these type of functions, what we're going to do is to manipulate these given integral. Okay? So we have the integral of x raised to 4 plus 6 divided by x squared dx. So what we're going to do is to apply linearity for this expression, for this fraction. What we're going to do is to expand x raised to 4 divided by x squared plus 6 over x squared. So we'll have the integral of the quantity x raised to 4 over x squared plus 6 over x squared dx. Okay, we just expand the rational expression. Next is we will simplify them, and while simplifying them, we will apply the sum rule. This is now the integral of x raised to 4 divided by x squared, that is equal to x squared, and then let's have dx plus the integral of 6 over x squared dx. Alright? So next is we will apply the power rule in this first term. We now have x raised to 2 plus 1 divided by 2 plus 1 plus, as you can see, for our 6 over x squared, we can factor out first 6 and then transform 1 over x squared into an exponential expression. So this is 6 times the quantity, or 6 times the integral of x raised to negative 2 dx. And we will also apply power rule for x raised to negative 2. But for now, let us simplify the first term. Na? So, x raised to 3 divided by 3 plus 6 times the quantity. This is x raised to negative 2 plus 1 divided by negative 2 plus 1 plus c. By the way, once you apply the differentiation rule, no need to include dx. You just have to simplify now the obtained values. So we have x cubed over 3 plus 6 times the quantity. This is x raised to negative 1 divided by negative 1 plus c. So simplifying this, we'll have x cubed over 3. And then this is now 6 raised to negative 1. This is negative 6 times for x raised to negative 1. Let's apply the law on negative exponent. This is 1 over x. And then plus c. Alright? Meaning, the antiderivative of the given function is x cubed over 3 minus 6 over x plus c. We have the integral of the quantity x raised to 4 plus 6 over x squared dx is equal to x cubed over 3 minus 6 over x plus c. Next example, this is the integral of the quantity 3x plus 2 squared dx. x. So for this example, what we are going to do is we have to expand this integrand first, and after which we will apply the rules of anti-differentiation, because we don't know yet how to find the antiderivative if we are dealing with, let's say, composite functions. So for now, we will have to expand this integrand and apply the rules of anti-differentiation. So let's say, for example, here we have the quantity 3x plus 2 squared dx. Its expanded form will be 9x squared plus, we have 4 times 2 times 3, 3x. That will be 12x, and then plus 2 squared is 4 dx. Okay, we just expand this expression, and that will yield to this polynomial. Next is by our sum rule of integration. We have the integral of 9x squared dx plus the integral of 12x dx plus the integral of 4 dx. By constant multiple rule of integration, we will have 9 times the integral of x squared dx plus 12 times the integral of x dx plus 4 times the integral of dx. Okay? So, by the power rule naman, we will have 9 times the quantity x raised to 2 plus 1 divided by 2 plus 1 plus 12 times x raised to 1 plus 1 divided by 1 plus 1 plus 4 times the integral of dx is equal to x of 4x. Now we will have to combine these expressions or simplify them. So 9 divided by 2 plus 1 is 3. So 9 divided by 3 is 3 times x raised to 3 plus 12 divided by 1 plus 1, that is equal to 6. 6 times x raised to 1 plus 1 is 6x squared plus 4x, and then your arbitrary constant. Don't forget this thing. Alright? So this is the integral of the quantity 3x plus 2 squared dx. For our next example, we have the integral of dx over the square root of the quantity 81 minus x squared. So for our solution, first is the same with what we do with the second example. We will factor out dx first. So this is now, let me copy first the given example. 81 minus x squared. So factoring out the x in this fraction, we'll have 1 over the square root of 81 minus x squared dx. And if you are going to check the given rules of differentiation, particularly for the inverse trigonometric functions, we have the integral of dx over the square root of a squared minus x squared, that is equal to inverse sine of x over a plus c, wherein a is any real numbers greater than 0. So as you can see, based on sa given example, a is equal to, or a squared is equal to 81. So if we are to transform this into um, a squared, our 81 will be 9 squared. So this is the integral of 1 over square root of 9 squared minus x squared dx. So meaning a is equal to 9. Therefore, its antiderivative will be inverse sine of x over 9 plus c. This is the antiderivative of dx over the square root of 81 minus x squared. Right? And then for our last example, we have the integral of the quantity square root of x times square root of x plus 3 over x squared dx. So for our solution, let me write first, we have here square root of x times square root of x plus 3 over x squared dx. So by sum rule, you have the integral of square root of x dx plus the integral of 3 over x squared dx. So as you can see, we have the square root of x times square root of x. And since they have the same index, we can multiply x and then x. So this will be square root of x. Let me write it here. Square root of x times square root of x means square root of x squared. And square root of x squared is equal to x. So more likely, we are getting the integral of x dx plus for our 3 over x squared dx, we can factor out the 3. And then for 1 over x squared, we have the integral of x raised to negative 2 dx. Alright? So again, for our 3 over x squared, we just have to factor out 3 in the numerator. We'll have 3 times 1 over x squared. And for 1 over x squared, just have to transform this into a negative exponent. So we'll have 3 times x raised to negative 2. That's why we have this expression. Alright, so applying the power rule, we'll have the integral of x dx is equal to x raised to 1 plus 1 divided by 1 plus 1 plus 3 times the quantity x raised to negative 2 plus 1 divided by negative 2 plus 1 plus c. So, simplifying this, we'll have x squared over 2 plus 3 times the quantity. This is x raised to negative 1 divided by negative 1 plus c. Or we will get x squared over 2 minus 3 over x plus the arbitrary constants. This is the integral of the quantity square root of x plus 3 over x squared dx. I hope that everything is clear now. But if you have questions, you may ask me or your subject teachers for further understanding of the lesson. Okay, so let me just go back to the objectives a while ago. In this video, we illustrate the antiderivative of a function. We talk about the definition of the antiderivative of a function and a theorem about the general antiderivative of a function. We use rules of differentiation given by these 6 presented examples and then compute for the general antiderivative of a function. So again, if you have any questions or clarifications about the lesson, you may ask or send email or your subject teacher. Thank you so much for watching.